next definition we'll need to examine our theorem is that of a field. Let F be a ring, then F is also a field provided that F is a commutative ring, meaning that it has multiplicative commutability. If F has a unity, E not equal to 0, meaning that F has a multiplicative identity, and if every non-zero element of F has a multiplicative inverse. Let's consider a few examples. Look at Z6. We know that Z6 has multiplicative commutability because 2 times 3 is 6 and 3 times 2 is 6. Modulo 6, that makes it 0, but it's both the same answer. We also know that Z6 has a multiplicative identity because you can multiply 1 by any of those numbers and you'll still get back the number you started with. Now, let's see if Z6 has a multiplicative inverse for each element. Let's just consider 2. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. Well, that's 0 modulo 6. 2 times 4 is 8. That's 2 modulo 6. And 2 times 5 is 10. Well, that's 4 modulo 6. Well, none of those were 1. That means that 2 doesn't have an inverse, and Z6 can't be a field. Well, now let's look at Z7. With Z7, we know it still has multiplicative commutability, and we know that it still has a multiplicative identity. But does each element have its own inverse? Well, let's consider 2 again. 2 times 4 is 8. Modulo 7, that's 1. So 2 has an inverse. Turns out that all of the elements in Z7 have an inverse, and that makes it a field. Now, why is it that 2 had an inverse with Z7, but it didn't have one in Z6? Well, that leads us to our next theorem. Zn is a field if and only if